Let's look at an example of an application of the hidden Markov model to speech recognition. So we're going to discuss the problem at a very simple level. The problem itself is very straightforward and well understood by everybody. If you have your iPhone and you talk into it, it takes your audio signal and it extracts the words that you're saying and puts it into text to then do some task. So speech recognition is a very straightforward problem. And the HMM is a fundamental approach to it. As you can tell from the title of the tutorial that I recommended to you by Rabiner, the classic tutorial, speech recognition is actually in the title there. So what the HMM does is it models transitions between basic units of sound in your voice called phonemes. So phonemes are thought of as the smallest unit of sound in a language that can be made. So English, it's assumed, it's thought has about 50 phonemes. And if you want a few examples of phonemes, you can look down here. So here's the words 0 through 9, and they're broken down according to phonemes. So 0 has about 4 phonemes, 1 has 3 phonemes, 2 has 2 phonemes. And each of these phonemes, for example, the word to has t and u. In each of these phonemes, it's thought that the same sound is being produced. So for however long I say t and however long I say u, my voice is making identically the same sound, or trying to make identically the same sound. There's some natural variation, but there's no change in the sound that's being made. And so 0 has 4 different points in that word where the same exact sound is being made at each of those 4 points. So what an HMM tries to do when modeling this is assign each state, or learn, it can't assign it, but it's hoping to learn for each state one of the phonemes. And so each state is a distribution on a sound f or I, for example. So if I say f or somebody else says it, we're not going to generate identically the same sound, but you could imagine that the sounds that we do generate will be very close to each other. You could say that they came from the same probability distribution on whatever the features are that are going to be extracted from that specific point in time. So let's look at how we actually process speech in one slide before we discuss applying an HMM to it. So we get this sort of a speech signal. So we have time, it's here normalized to be between 0 and 1, and the speech signal is an amplitude, and there are many measured values between 0 and 1. We then extract features from this using the Fourier transform along a sliding window. So at different points in time, we expand a window. For example, at this point here, we expand a very small window, for example, perhaps 50 milliseconds between around this point. And we then look within that 50 millisecond window at the audio signal at that time point and extract a feature vector for it. The first feature vector that would be extracted and then possibly post-process would be the frequency content. So imagine that we look at about 10,000 frequencies. We get a breakdown at any given time point of what frequencies are being used. So at this time point, it's very quiet, corresponding to this point here. So there's almost no sound being made. Then suddenly there's sound, and we get a frequency breakdown that looks like this. So at this time slice, we have a lot of this frequency here, some here, here, and then less other places. So this is the distribution on the frequencies over a sliding 50 millisecond window. And so you can see it's very smooth. I believe what's said here is Bayes' theorem. So this is probably Bay and then S and then theorem. And so what's happening is you can see that there's very smooth transitions between Bay and then S. So this would be one phoneme. This would be, I suppose, 2 phonemes. So at some point in here it would have changed. And then theorem. For example, this could be the, and then suddenly it changes to and then rum. So we have these different, we have this sort of a frequency content. And then using things like MFCCs, mel frequency kestrel coefficients, or other feature extracting techniques, we can then reduce this to being a sequence of, for example, 40-dimensional vectors. So we have a feature extraction process where we have a sequence of vectors, and each vector is intended to capture the frequency content at that moment in time. And now we want to use a hidden Markov model to model that frequency content sequentially. So we could either use a continuous hidden Markov model, in which case if we reduce this down to 40 dimensions using MFCCs, we would then perhaps say that each state has a 40-dimensional multivariate Gaussian associated with it. And for example, all data generated in this time period would be potentially in the same state with perhaps a small change here, and therefore have the same distribution on these different vectors, and so on. If we wanted to discretize it, we could use k-means, and so this is often where k-means is extremely useful, and it's I would say one of the most practical uses for k-means is in discretizing data for use in other modeling problems. So for example, if we had a training set like this of many different instances of a person speaking a word, and we extracted a sequence of feature vectors in some space, d-dimensional space, we could then take this data and quantize it using k-means to get a codebook of size v, where each vector in that codebook is going to mark off a region in the space that the data lives in RD. So then we learn this codebook, and we represent each of these signals as the sequence of which codes it was assigned to. So we learn a codebook, we get a new signal, we quantize each column by assigning each column to the nearest centroid, and then instead of reporting the sequence of d-dimensional continuous vectors, we simply represent this sequence as a sequence of centroids. So for example, we could say the first two centroids were cluster 2, the third vector in this sequence was mapped to centroid 6, and then the following 3 vectors in this sequence was mapped to centroid 4, or something like that. So we've taken a d-dimensional sequence of d-dimensional vectors and quantized them to now represent each signal as a sequence of discrete values. So we could now transition to a discrete HMM for this type of a model. So let's now look at a simple speech recognition model. This is not the state of the art. This is not what your iPhone's doing. This is, for example, a scenario where we're doing an automated phone conversation, like where you call your credit card and you tell them names of countries that you're going to be traveling to, something like that. And they want to extract that. They want to recognize the names of those countries. They want to recognize the purpose of your call. So a simple question-answer format. What we have as training data are quantized feature sequences of the different words that we want to model. So we have many instances of a person saying yes, no, travel, and we quantize each of these sequences. And so then what we do is we learn an HMM for each individual word. So for the instance of the word yes, perhaps we have hundreds of thousands of instances of a person saying the word yes, and for each of these we extract a sequence, and now we want to learn an HMM that models the sequence of the word yes. So we learn an HMM for generating the word yes. We learn a different HMM for the word no. We learn an individual HMM for each word that we're interested in learning. And then we have an HMM representation of all the possible words that we think could occur. And if we, for example, don't know what was said, we would say tell the automated system to say, "I'm sorry, repeat again," something like that. And so now what happens is we want to predict a word. The automated system asks a question, it hears yes, it captures the yes, it extracts the features from the audio word yes, it quantizes the sequence yes, all of this done very, very quickly. And now it wants to say what is the word that corresponds to this quantized sequence. And so what would it do? What we want to do is we want to say, what's the probability of this new sequence of that I have? We'll imagine it corresponds to yes, but we don't know that because it's an automated system. We calculate the probability of the sequence given a particular HMM. Imagine that we want to know what we want to query, whether this word that was said corresponds to word W. So we take the HMM we learned for word W, we calculate the probability of the sequence given the word W, which requires the forward-backward algorithm because we've integrated out the state sequence, and we get the probability of that sequence given the HMM for a particular word. We do this for every word, and then we define, or we assign the label for this sequence to be the most probable word. So we simply pick the HMM that most likely generated the sequence that we've observed, and that HMM will correspond to a word, and we declare that the word spoken was that particular word. So this is a very simple example. And notice that what we've actually done is define a Bayes classifier here. So this is an example of a Bayes classifier where we have a uniform prior on all of the words. And we might want to improve this by learning the frequencies of different words and having a prior probability on each of the words, and then multiplying this by a prior. So this is actually what we've defined here as a simple Bayes classifier. Notice, however, that this is much more complicated than the Bayes classifiers we thought about previously. So in this case, what we had to do was for each of the potential classes, of each word is a class now, we had to learn a class-specific model that was much more complicated than a simple multivariate Gaussian. So we had to run a more complicated algorithm in order to learn the parameters of this class conditional distribution. And in this case, the class conditional distribution is an entire model. It's not simply a distribution on one vector that is like a multivariate Gaussian. It's an actual model for generating a sequence of observations. And so we could have actually, if it's a Bayes classifier, we could have tried different things. We could have tried a Gaussian mixture model if we thought that there was no temporal information worth modeling. We could have simply treated the original vectors as if there were no time dependence between them and learned a word-specific or a class-specific Gaussian mixture model, in which case we would calculate the likelihood of all of the features extracted for the incoming audio signal given that Gaussian mixture model. And so we could have tried that and seen which does better. However, the HMM most likely, because it takes into consideration a sequential information, we anticipate and observe that it's going to outperform the Gaussian mixture model, because in this case we've chosen a more appropriate class conditional density or class conditional model in this case.